Now that we have our conceptual data model and our application workflow, we combine them to make our logical data model. That's what we'll discuss in this section. Here's a diagram to explain it further. We have our conceptual data model on the left and our access patterns on the right. Remember, our application workflow diagram had access patterns in it. That's the actual queries we perform against our Apache Cassandra database. That's the critical part to take away from your application workflow diagram and mix that up with the conceptual data model to build our logical data model. That's what we have in the middle here. We apply some mapping rules with inputs being our conceptual data model and our access patterns, and out pops the logical data model. We call these Chebotko diagrams, named after the person who came up with this way of diagramming your logical data model. You can see it looks a lot like our application workflow. At the bottom of the slide, you see query 1. Find a video with a specific video ID. Looking at the Chebotko diagram in the middle, you see that query 1 leads into a table which would satisfy this query. We'll get into the details a little bit more later. Let's get some terminology out of the way. First of all, you'll notice this diagram looks a lot like our application workflow. Hence, that's why we built our application workflow. We have our queries, which are the arrows leading into the table. We have our table diagrams, which looks a little bit more like Cassandra tables. Hey, we're getting there. And then at the bottom, we brought along our query list. Again, the queries are fundamental when it comes to data modeling with Apache Cassandra. On the right, we have our UDT diagrams. UDT stands for user-defined types. These are a lot like tables, except there's no primary key. We can nest these structures in other actual Cassandra tables. We'll get into the details more later. In order to move from a logical table diagram to a physical table diagram, you only need to add the data types. There's a little bit of optimization that we'll get into later, but let's look at an example. Here's our table. You can notice that we have some abstract column names on the left. On the right, we describe whether they're partition key, clustering column, static column, so on and so forth. Note the notation on the left corresponds with the description on the right. For example, in order to do a list, which is column name 7, we use square brackets. In order to do a set, we use curlies. Hey, you want to do a map? Great, angle brackets work just fine. The key thing to pull from this diagram is that we add the CQL types in the middle. That's where we get physical. Once we have our CQL types, we can write our create table statements in Apache Cassandra. One other important thing to notice in this slide is that our column name 1 has partition key, which we denote with a capital K. Clustering key columns we denote with a capital C, and we also denote whether they're sorted ascending or descending with a small arrow next to that C. Remember, we're modeling in order to satisfy some queries. The partition key and clustering columns are critical to get correct. Remember how I mentioned we'd talk about UDTs later? It's later. UDT stands for user-defined types, which is essentially a table without a primary key, but you can nest that type within other tables. For example, with the videos table, we have an encoding column third from the bottom. That encoding column represents how the video data is stored in the video data file. There's a lot more information than just some simple text to store here, so we encapsulate all that in the encoding user-defined type on the right. Notice it has encoding, height, width, and possible bit rates. The same is true for actor name. Remember when we saw actor in our conceptual data model, it was a composite attribute? We can also break it down into first name and last name in the logical layer as well by having an actor name user-defined type. This is where the artistic part comes in. Maybe you want a separate first name and last name column. Maybe you only want one column to store the first name and last name in instead. It's up to you. But just know that there's these user-defined types that you can utilize to help you move along. Here's the exact same diagram, except it's a physical layer diagram. Let's pop between this and the logical diagram we saw in the previous slide and see if we can tell the difference. Logical, physical. Logical, physical. Do you see the difference? Go figure. Hopefully it was obvious. As I mentioned earlier, all we're doing is adding the CQL data types. Here's an example logical data model for our killer video domain. Notice we have our application workflow, we have our queries create our access patterns at the bottom. I encourage you to pause the video and study this diagram just a little bit to get familiar with it. Here are some basic rule of thumbs when doing data modeling. Know your data, know your queries. You can also nest data, and you've probably heard with Apache Cassandra, we duplicate data. We sacrifice space for time. We want our queries to perform. So what do we mean by knowing your data? Well, you can learn about your domain by doing the conceptual model process. If you're like me, you just want to get in and start coding, create some tables, let's just roll and not think about it. But every time I move forward without doing any upfront planning, it always ends up biting me. It's good to take a little bit of time, talk to your domain expert, and become familiar with the domain that you're going to work in. One part of understanding your data model is understanding the primary key constraints. Again, a primary key in Apache Cassandra is composed of uniqueness and also to satisfy a query. Often in a relational world, we get so tied up in the uniqueness that we even forget that queries exist. But in Apache Cassandra, we flip that over and actually worry about the queries first and then add uniqueness on the end. Look at the example we have here. A videos table by itself has video ID as the primary key. This is a typical table you would see in a relational model. You may also need this table in your Apache Cassandra model as well. However, the table on the right, videos by user, the primary key has a user ID so that we can look up the videos for a particular user, and then we've sorted by the uploaded timestamp. We tag video ID on the end simply to maintain uniqueness. Remember when we were talking about keys for our relationship types? Again, remember the cardinality of the relationship type determines the key for the relationship type. By building the application workflow diagram, you now have your queries. That's critical to understand what you need in your data model. The most optimal situation is when you create a table that can satisfy a query, and that query only needs to execute once. We call this single partition per query. This is the most efficient design pattern in Apache Cassandra. It's basically constant time, because when you query for that partition, you simply give it a partition key value. The coordinator knows, figures out which node has that value. That node retrieves the data and returns it right back to you. There's no filtering or searching through the entire cluster. It's really just go here, pop there, give the data back. Some access patterns may require multiple queries on your Apache Cassandra cluster. This isn't too bad as long as you're not pulling from multiple partitions at the same time. Getting away with a few partitions is okay. Doing several of these means you're doing something wrong. Here's the anti-pattern you absolutely want to avoid. Searching through the entire cluster, through all the tables, through all the partitions to pull back several rows. Remember that allow filtering that pops up in that warning if you don't do your query right? Yeah, don't use it because this is what will happen. Essentially, you're stressing out the entire cluster, telling every node, hey, I need some data. Please go do a linear search through everything you got. Not a good idea.